screen now?
Yes, we can.
Okay, so here's our group member at the bottom of the video, and now we should start it. We also do about the surface area and the volume of the sphere.
The topic of surface area and volume of a field. We will now talk about the volume formula of a field and how we obtained it. We have the following graph which can be drawn using the general formula of a field in 2 dimensions, or a disk. X squared plus y squared equal to r squared. By spinning this disk around the y-axis, we will obtain a field. So now we can obtain the area of cross-sections, which is A equal to pi y squared. We can also spin it around the x-axis, however, it would be A equal to pi x squared. We generally spin it around the y-axis as y is usually written as function of x. We can write this area formula in form of derivative of volume, dv equal to pi y squared dx. By integrating both sides, we have the following. Integration of derivative of volume will give us volume, so the volume formula can be represented by these integrations. Hence, a volume of a field created by spinning this disk around the y-axis is 4 pi r cubed over 3 after we done the integrations.
We will now move on to the equation of surface area of the sphere. To prove that the surface area of the sphere is 4 pi r square, we first need to know the arc length of a line in integral form. For equation of a semicircle, the integral is to integrate from b to a of square root dx squared plus dy squared as shown. Then we can get the formula of the surface area of a sphere by rotating about the x-axis, which gives this formula. The circle is then parameterized and sub in giving it this equation. Hence, solving this equation will prove our statement.
Okay, so I will explain the derivative of it. So we have first divide the dv is the represent the chain of the volume, the dr will represent the chain of the radius, and dv over dr represent the chain of the volume respect to the radius. So a sphere is built up or constructed by stacking multiple thin shells, and each one of them has a tiny thickness dr. The chain in radius generates a small increase of the volume, which is the volume of the extra shell. So if we can calculate the volume of the extra layer, we can determine dV given dr. As a result, the volume of the shell with the inner radius is with the radius r is dV equal for third pi and the division between the radius. And if we expand it out, it will be r cubed plus 3r squared dr plus 3 r dr squared plus dr cubed minus r cubed, and then we also down because we can see in here the dr is just a small number change in the radius, so dr squared and dr cubed is even smaller, right? So we can ignore or skip to the value of dr squared and dr cubed, and from then the dv equal to 4 third pi 3r squared dr, and then become dv equal 4 pi r squared dr, and from that we can conclude that dv over dr is 4 pi r squared, and it is the derivative of the volume respect to r is the surface area of this.
To answer the question of whether the relation holds for high dimensions, we look at the following formulas. It is important to consider that d equal to the number of dimensions in these formulas. So we have the surface area and the volume. It is also important to consider that these are unit spheres and don't show the radius of r. So r grows as r to the power of d. So if the dimension was equal to 4, it would be r to the power of 4, and if the dimension was 5, it would be r to the power of 5. In the next example, we use d equals to 5 and sub them into these formulas. Looking at the right-hand side first, we see the volume formula where we get 8 pi squared divided by 15. And for the surface area, we get 8 pi squared divided by 3. If you consider these two carefully, we can clearly tell that if we differentiate the value on the right, if r was to the power of 5, we get same value for a. This shows that a equals to dv over dr, which proves that the relation applies to high dimensions for a sphere. It is also important to consider that as d goes to infinity, the volume of a unit sphere also goes to 0. Thank you.
Okay, thank
Okay,
you, guys.
that's the end of and now one more thing, Jason.